to first apologize because of the time constraints and the schedule that I have to teach here, that I couldn't really um, attend in person. I very much look forward to going back to Montreal, but it not meant to be. And also, I learned a lot from watching a lot of videos, even though I couldn't attend the meeting in person. Um, a lot of this very nice work and recent development of mean field game. And I felt this is so valuable for many of these, not only us working in mean field games, but also for people. There's a trend among the young generations to move on from classical control and game theory to machine learning. And I think this is a very important venue to actually for us to learn what is the latest development and then to really get the discussion going on in this hardcore theory or mean field game. And also, I would like to take this um, chance to actually do a little bit of advertisement that in May 23 and 27 in Chicago, which is the new Institute of Mathematical Statistics and Machine Learning. There's a workshop that is really on mean field games and machine learning. Okay. And so this is, if anyone interested, please register and then or send email to me if you wanted to make contributions to the workshop. And I think one of the purpose of this workshop is very much aligned to what I'm going to talk about in this talk. The trend of moving from hardcore stochastic control to machine learning should be very carefully followed in the sense that it's very important to actually take a machine learning theory and a mean field game theory and say take a master equation and then try to take a machine learning techniques, say, okay, there's a neural network, there's an actor critique and so on and so forth. And then let's apply this machine learning techniques to solve the mean field game. And I think that's a one way, and it's an important one way in terms of the traffic of the scientific communication. On the other hand, I think it's also very important, just very much like the development of math finance and with mathematics community, the other important direction should be also to take a problem from machine learning and then to see what are the key elements in those problems and learn the languages in machine learning so that you can communicate with that community and then see what are the challenge for the mean field game or for the control community to develop appropriate foundations, including concepts, including theorems, including techniques to really develop the foundations of machine learning with the tools that we can develop here. And you will very quickly find out that there's a gap of what has been developed in mean field game theory, for example, and there's a gap and the theory of machine learning. And there's a very exciting direction where you can develop both the techniques and applications. And this is very much what I'm going to talk about here, which is I'm going to start with a very simple example and show that with this multi-agent reinforcement learning, which is a hot topic in machine learning, and where is this mean field really comes in, and what is the gap that mean field cannot really easily be applied to this kind of problems, and what are the challenge we have to do. And in order to really talk appropriately these problems, I probably also have to review a few fundamental key concept that has been developed in the framework of this mean field multi-agent reinforcement learning. And I've seen a lot of talks, including Renee's talk, including Matthew's talk, including Sarah's talk. It has touched upon a few concepts here and there. And I wanted to basically put a strain to put all the things in a historical perspective. Okay, so this is a joint work based on a group of brilliant students that and postdoc I was very fortunate to be able to work with Hao Tiangu, who is actually a math student from UC Berkeley, and Xiaowei Li used to be the postdoc working with Hui Yinfan, and now a student of Hui Yinfan and a postdoc with me for a couple of years, and now moving back to China. And Ren Yuanxu is actually now used to be in doing postdoc in Oxford, and now is actually assistant professor at USC. So you can see that this is actually a work over starting from 2019 and including a series of published papers that I'm going to refer to later. Okay. So just to get the thing right, I'm going to touch upon some of the development of what is the multi-agent reinforcement learning in the context of mean field games. And in particular, for the problem I'm going to talk about is going to be mostly in the domain of mean field control, and of course with the learning component. And the challenge of to solve this problem is exactly what I talk about, is what are the gap between what mean field control can be brought to, and what is the reinforcement learning is really asking us to do. And this gap is actually we have to really look at the problem and look at the problem structure and design new techniques and approaches in order to design algorithm that is of interest to the problem and to the community of machine learning, and also provide mathematical proofs of convergence analysis and sample complexity. And that's, I think, is the strength of this community that we can actually really make a significant contribution to. You have seen quite a bit of this machine learning talks in this conference that with very sophisticated models, starting with stochastic differential equations, and then you have master equations, or you have anything with common noise, and this is a very complex models. And to really get the concept right, I think we will start with a very basic model, okay, and see what is there, okay. So I will start with the example of the multi-agent reinforcement learning. And I will review, as has been reviewed, about reinforcement learning and Q-learning. I'm not going to touch those that has been studied, but I want to point out what was missing in the development of the whole theory here, okay? And then I'm going to start talking about the key element in the framework that is leading to solving this problem, and then the new development that help us eventually settle down to get some desirable results in terms of convergence and complexity analysis for reasonable algorithm design. So talking about algorithm design, I want to actually make a remark. You know, I came from a control background, and whenever I was thinking about algorithm design, I always thought that was numerics, that was, you know, low-level mathematics or CS stuff. It's interesting over the years after I learned this machine learning to realize that there are a lot of interesting probabilistic techniques that we can develop here to actually help analyze this. I have to say that it helped when I learned all this subject and started working on the subject. It helped to correct a lot of my own bias against this whole field. Okay. Um, so let's start with this motivating example. This probably is everyone has more or less experienced at some point, which is you call Uber and you want to have a ride. And this is from our perspective as consumer perspective. But if you actually looking from a perspective of the platform that controls the dispatch of this Uber fleet, then you actually see, you can very much see that there are important information going on here, which are, you see the driver's information, who are available, who are not, and their locations, and you see the orders that actually has essentially the origin and destination, okay? And from a platform perspective, you of course want to improve the efficiency, and well, you also want to make your business reasonable to maximize your profit or maximize your revenue. So, and then of course from this driver's perspective, and if you see all these drivers or at least from a consumer perspective, there is this homogeneity. In general, I really don't care about the name of the driver. I really want to have a driver with this reasonable price that will take me from A to B. Okay, so this, you look at these problems, it's a very natural background where the mean field game should be having some say in this. Okay, and then you look at various other examples, including online advertisement that you know is very popular. It's a base that Facebook and Google and all the, even Amazon now has a huge, which I'm working for, is having a huge platform that is managing this online ad. And also, this is actually from the platform perspective, you see a lot of advertisers coming in, and then you want to manage this. And this is really a central controller's perspective. In a way, it's collaborative game. And of course, you also can view the Zoom meetings, and then you think about automatic drivings, and you see in finance, the so-called crowded short, and so on and so forth. There are different perspectives of this large population that are interacting, and depends on your perspective, you can see them as either collaborative or competing. Okay. Going down to this, let's not do this open loop, closed loop, continuous time, everything. Let's just look at the simple framework and see where this learning is really coming into interacting with the control or games. It's really, if you go to the very bottom of reinforcement learning, it's nothing but going back to this counterpart of Markov decision processes, okay, in a discrete time, where you have a underlying stochastic system that really depends, it's the transition matrix we are familiar with. And of course, the decision problem is when you talk about Markovian, you have functions that match your state to a decision variables. Okay, and then you have the objective function that really maximize if you take an infinite time horizon, or you can take finite time horizon. Then you have a very easily written down reward functions that you can depends on the state and depends on your action. And this is really discrete time stochastic control problem. Okay, we know that. So this is probability 101. And probability 101 for reinforcement learning is just saying that, well, whatever you have here in a Markov decision problem or in the discrete stochastic control problems, the only difference when you move on from control to learning is really you consider that the probability transition and the reward are possibly both unknown or part of them unknown. Okay. So in order to translate this whole thing from the Markov decision theory to the learning, there's a very important vocabulary one has to also to think about is really in the control. If you're looking at deterministic strategy, it's what we call control or strict control is really mapping the state to the action. Okay, this we know. The difference in reinforcement learning is actually they randomize this control. And this is not new to control theorists. This is called relaxed control, which basically is saying that you actually take a state, you actually look at the distribution of the actions, and you take a randomized strategy. Or in game theory, it's also called mixed strategy. Okay, so these are vocabularies that if you want to really make serious dent to the theory of machine learning, we have to learn the vocabulary. And then this optimal decision in the reinforcement learning, it really depends on the optimal choices of this randomization. And that's really what exploration and exploitation is coming from. Okay. So what is essential about this is, in contrast to these controls or discrete control or Markov decision problems, instead of looking at a value function, which we really pay attention to the state, that's why we call it Markovian decision, it's really you look at not only the state, but also the action. And this is called Q function. And this Q function the entire development of reinforcement learning from single agent to multi-agent and now to mean field is very much really built on the building block of Markov decision problem, and the building block of which is Bellman equation. We cannot bypass that. That's a DPP, okay? And the DPP here, in analog to that Markov decision problem, is this DPP for Q function. And you look at this DPP function, you actually say, wow, this is straightforward. Okay, we just, instead of just looking at the state, I just look at a pair of state and action. And so everything goes smooth, and this is very important because if you think about the intuition behind reinforcement learning is not only you want to know what are the optimal things you will get, but also you learn. And by learning, you really wanted to take this knowledge of actions and how you get to that level of knowledge. So this is decoupled with this action. So you learn through taking actions, and your action give you the learning curves, okay? And so this Q learning update is just basically the exploration and exploitation, which is really the randomized way to ensure that not only you are happy with what you have now as an optimal value, but in the meantime, you're exploring some unexplored territories or actions so that you can go along the way so that to ensure that eventually you get the convergence. Of course, in this design, immediately you have the question very much in the parallel of Markov decision problem where you say that, well, do we have the DPP? Yes, there was this very nice papers that was developed in parallel to this DPP for value function. It's also DPP for single agent Q function. And also, of course, there's very nice papers that I forgot to put in here is that when you do the exploration, what are the appropriate learning rate that you should put in to guarantee the convergence of the Q function. And so there's a series of problems that immediately arise from the machine learning perspective, okay? Now, if we understand reinforcement learning and we understand the parallel of development, the challenge is really in multi-agent reinforcement learning, where when you consider an agent, like the example I talk about, the ride sharing or the online advertisement or Zoom meetings or many of these examples, it's really we're talking about N, which is pretty large. And the fundamental question in the machine learning community is actually designing efficient algorithm with guaranteed convergence or with understanding of sample complexity where you actually can analyze this problem. And if the naive or traditional way of multi-agent reinforcement learning or the techniques are really exploding with respect to the dimensions of N, okay? So this is really the last three, I think from 2019, our paper really developed into a huge field. Now, this is where the mean field game is really come from. Of course, it's a natural thing to think about in all these examples. We can easily say that borrow the ideas from mean field games. We can assume the homogeneity. We can also assume the weak interaction because the drivers may not really care too much about the individual other drivers, but he's more worried about the traffic situation, which you can think of this as a first order approximation of this mean empirical distribution. And so this is a very natural breeding ground from n-player games where when we have the mean field games, then we actually naturally can look at it in the learning community, in the learning context of this. Important thing arises here is just as following the mean field game development, the learning field for mean field game also grow in two paths. One is the mean field, which is you actually take the perspective of individual drivers and you think about Nash equilibrium. And the other one is actually you take the central controller's perspective where you take the Pareto optimality as a social efficiency criteria and you end up into this learning with mean field control. So this is a very partial literature, but just to give you a historical perspective of how the field is evolving. In general, the since 2019, when we were struggling with that paper of learning mean field games, we didn't even know how to put properly the framework and how to do it, but and then how to really make it accessible to the mean field, to the machine learning community. But over the years, and we actually benefit a lot from reading a lot of machine learning papers in that community. Over the years, though, you actually see that this has mushroomed in this particular learning mean field game, this perspective. There are a lot of algorithm has been developed in not only linear quadratic, but not only in the case, the very simple case we started with the discrete. Now it's actually going into continuous time. People are starting to use various very sophisticated techniques, and there's an army of people working in this field. Okay. In contrast, even though we have heard a few talks here in mean field controls based learning, in fact, the foundations there was really not built properly until quite recently. Of course, the same thing in parallel to Markov decision problem, we also struggle a lot, and we have to find counterexamples to convince ourselves what is the correct, instead of value function, what is the Q function that has to be designed. I'm going to touch upon that, especially in the example I talk about. And of course, then there was this beautiful paper that René also pointed out, that extended our discrete time versions to the continuous time versions. Okay, and by the way, from that DPP that was really establishing this, then the natural next, when you look at machine learning, is actually looking at algorithm design. And by the way, the paper that was talked about in this paper, we don't really have the proof of the algorithm, and there's a companion paper here that is published now in Science Data Sciences that is actually has all the proofs of this algorithm convergence and complexity. Okay, but it's actually a journal paper. It takes a long time, but it's actually at the same time we were writing this too. Okay, in any case, if you look at this, and of course there's a very interesting papers that recently come up here that is trying to bring this two perspectives together in terms of understanding mean field control and mean field games in the learning context, and how this two can be connected using a time scale difference. Okay. So this is just a basic perspective of what's going on. And what I wanted to say is essentially what exactly is difficult right from the beginning when we were struggling was really you take this just as earlier MDP problem, you throw in very naturally the empirical distributions, just as in mean field games. And of course, here is a learning concept here. And so naturally, you still have this unknown transition matrix and transition unknown reward function. Okay. When you actually look at the representatives agent, then you actually take over all the distributions and over the infinite time horizons. And the difference here, though, if you actually think about it, the difference of mean field control and mean field game, as I think Matthew also talked about, is in terms of algorithm design, there is much natural why mean field game is much easier to think about in terms of algorithm design, because the fixed point method in mean field game is a very natural recipe to design algorithm, because you can simply change the first step of the MDP problem into reinforcement learning, and then you can build upon this fixed point method, and that's a very natural way. Whereas when you look at the mean field control, we know that in mean field control, in order for DPP, this is earlier work, of course, the Hui Fan and Wei, when they were actually studying also started from the discrete time about the DPP is what is the dynamic programming principle? What is the time consistency here? And of course, there's also very nice talk about on the Stackerberg. There's also this time consistency. It was not obvious for people to first time to look at it to see what is the right state space for the time consistency to hold. Okay, and this is beautiful paper of 2000, I don't know, 2018 or somewhere even earlier, that they have a series of papers from the discrete time. And the idea is really lifting the space from the space to the probability distribution of the action of the state space. And therefore, from there, you have these empirical distributions that is becoming deterministic flows in this framework. And that's a key. And the first thing for us to say that it's reasonable to actually build this mean field control to this to as an approximation to the multi-agent is actually in the learning concept is actually to show that just as in this without learning, there's a sufficient approximation errors that or desirable approximation errors that we can deal with. And of course, this is very easy that you actually see that many proofs is very much following the classical mean field game. Now you can show that in that learning context, the error is also in the order of 1 over square root of that. Okay, so that's the first ingredient. The second ingredient, which was not so obvious, it was supposed to be simple, was if you look at without learning versus learning, from Markov decision problem to the Q function, we know that this has to be from the value function to the joint or the pair of state and action. And when you actually look at in our Markov mean field control perspective, we know we got wisdom from Wei's and Huiying Fan's earlier paper that it has to lift from the state space to the empirical distribution. And of course, now the question is, what is this lifting is going to be about? This lifting is actually important. It's not a simple lifting. Here, the lifting is when you think about a central controller of mean field games, or mean field from a Pareto perspective, you have a central controller. And if you think about the policy or the controls, is actually the policy depends on the ST, and also it depends on the empirical distribution. And of course, then you look at these, you look at the empirical distribution, you look at the state, yes, and you look at the empirical distributions. And when you actually have a central controller, what information he has, he actually can see the distribution of everyone. So the correct age here in terms of lifting has to be assuming that he can see the empirical distribution, and then he actually give you the action that is fixed on this S and with the empirical distribution. He see the flow of the population. And once you get this H set right, this H becomes very critical for this Q function consistency to be established. Once you have this, you have this set of local policies that depends on distributions of actions, then you can write down the dynamic programming equations for the Q function, very much like what you have done earlier for many of the Markov decision problems, except when you look at these Bellman equations, you should not call it as a Q function anymore. You should call it integrated Q function, integrated in several sense. One is, of course, this second argument, as I just talked about, you actually, as a central controller, you see you have you see the ST, and you see the empirical distributions of the population, and then you give the command, and the individual player will follow your command. And this is a very, in a way, localized execution versus the decentralized command. This idea is actually turns out to be extremely useful for applications that I'm going to touch upon. The other one is actually when you actually do this kind of H integrated over this S, then the aggregated reward function here should be aggregated over, this is your reward function, aggregated over this mu as well, over S and A. And similarly, you don't just look at the one-step transition matrix of what you would have set in the multi-agent setting. You should also aggregate it over all the S and A in the sense of with the weight of this mu and H. So this is actually very important, but it's actually quite natural if you actually look back. But before you see it, how you actually reconstruct this DPP so that you get the correct Q function was not obvious. In fact, there were very various papers that we pointed out, and then that's why we have to give a counterexample in this paper to show that many of the existing Q function was wrong, and I guess many of the subsequent papers were corrected because of this. Okay, an important thing, of course, is once you define this, you still inherit the beautiful results from mean-field games, where mean-field controls or Makin-Volossov controls, where you have this flow property of the mu t that was critical in this no learning context where you can establish the DPP. Okay, but so this is actually the ideas that I'm laying out to show this is another element where we could help for this machine learning community to really properly set the foundation right to say what are the right framework to work on in this multi-agent reinforcement learning. And not only is just for the mathematical satisfaction of establishing the DPP for the IQ function, but it's also this insight of this DPP, as I alluded, is in fact, you can see there's already of this in the mean field control perspective, already this local natures of the problem versus global picture of problem. There's a Q function that you actually can aggregate it from the local Q function. And that turns out to be extremely useful later on when we're going to solve these network problems. And also, when you actually have this kind of Q approximations, you can design appropriate neural networks so that you can guarantee efficient sample convergence and sample complexity. Okay? So this is actually, I just spent a lot of time, about half of the time to set the thing right. Now we come back to this. Yes, coming from what we can borrow from the mean field theory is actually we can develop in parallel of all the theories of DPPs and Q functions and set it right. And of course, if you now go a step closer to the designing of algorithm, that's what we should be doing in machine learning is you realize that in terms of design algorithm, sometimes it doesn't fit with the application. For example, when you actually think about the Uber applications, you don't need this Q table to know everything about the distribution. You just need the local information, or sometimes you just don't even know the global information, okay? And also, there are many structures that has been ignored when we do this mathematical averaging from mean field, multi-agent to mean field, okay? So what is this really the nature? So let's revisit the problem that I just talked about. When you actually think about the ride hailing, the order dispatch problems, we have this. We know that this is a corporate game. And we know that this is a large population. And we have the homogeneity. And we also know that there's an interaction. Not only they are weak, but they are, the driver probably just see from the map overall traffic information and then his neighborhood. And he will care mostly about where his route is going to take him. He may not, a driver from San Francisco to Berkeley would not care too much about the Bay Area in general. Okay. And so this part is how we actually cope with this kind of partial information. And also, the most important thing that I'm emphasizing in this talk is the network structure. If you think about whether Zooms or whether we're doing the ride sharing, there's a network structure. And also, this network structure is very different from the network structure that has been popular, in CS for many years about Facebook. In Facebook, what they utilize is the network structure of humans, of agents. Okay, it's important to know where my friends is and what they have been doing. Whereas when these network structures, the drivers, they actually move, and what really you actually care about are actually the state. So you actually look at I need to go from the airport to the university. I really care not too much about the state of the driver. I really care about the state of this particular region. And we call it the network of state. Okay. So think about this. The difference is you think about buying houses. Who reside in that house is not important. It's actually that house location. Okay, there's an analog here. So how do we actually to catch up with the last piece of this network structure to really design efficient, attractive algorithm so that we can actually really convince people mean field game is a powerful tool to really design this, rather than just applying neural network and solving our master equations. Is actually, let's build a network structure and see what we can do. Okay, so now you think about general, almost what you're familiar with in any graph theory. You have an agent that you can think of as a node. Okay, and the agent share a finite state space and takes finite action. Okay, so I always take the easiest problem that we don't understand. And then you consider this network on this space where you have a directed graph, undirected graph. Okay, so you actually think about this is the set of edges, epsilon, and then this is your node, this is your edges. And similarly, in the graph theory, what we do is we call the distance between the two nodes is the number of edges that are connecting in the shortest path. It may not be unique to get the same distance, but it could be multiple, but the distance is well defined. And also, I borrow the idea from graph theory, which I look at the neighborhood of a particular state. And of course, I can look at the k-hop neighborhood, which means the distance of k. Okay, and if I think about the drivers, this Uber's problem, I really care very much on the traffic situation of this neighborhood, and depends on, I need to see from going to airport and to the campus, then probably I know there's a key intersection or key neighborhood, key states, key points that I have to go through, that I have to worry about. Okay, so this is the important, it's a K neighborhood. And now the question is, when you have this, how you actually can keep learning this from what we started with. All this algorithm, as I said, reinforcement learning is such a rich literature. It's really built on the vast literature on Markov decision problems. And many of the algorithms, whether it's an actor-critic or anything, is really still about value iteration, about policy iteration. Okay, so this is our very important foundations. So how you actually do this to design algorithm when you build a network structure of this the key thing here is you think about reformulating this Markov decision problem or discrete control problem into a team game. Why I do this? Because I look at this team game, I can hopefully truncate the huge, big Q table, which enumerate all the state and all the actions into a much smaller one. Why is that? Let's see this picture. If you think about the system here, you have many agents and they are actually moving around through the state. If I do regroup all this, I'm going to look at state 1 and I put all the agents, all the drivers that are in state 1 in one place. And then I put all the drivers in state 2 in one place, okay? And now instead of looking at all the drivers hanging around in San Francisco, I just look at a few places that, or a few critical places I need actually to use that is important for me to move from one to the other on my route, okay? So in this case, instead of looking at multi-agent games with n players, you're looking at as teams. The S is the state of the system. And in general, when you actually, this reformulation is efficient when you have a large population where the number of a state is much better, much bigger than the teams. Okay, so the number of agents dominate the states. And of course, once I do this, I need to make sure that I can reformulate it from one Markovian system to another. And the way to do this is you actually think about this. The reward is going to be determined, and this is reasonable, to determine on this state and the empirical distributions of his neighborhood, okay, and the action of him. And the same thing as the transition matrix, they're going to be appropriately modified. Once I have this, then I can reformulate this big multi-agent reinforcement learning problem into a smaller Markov decision reformulations, okay? And this will allow us to do everything in the language of team state, team policy, team dynamics, and team reward. And the most important thing is it allows me to decompose the huge Q table that is actually Q functions of all teams is decomposing into smaller Q tables that is actually based on the team situations. Okay, so I think this is the key idea. So this is the ingredient that we have. And of course, because we have built the general theories about Markov decision, mean field controls in the context of learning, so we can now, once we reformulate this, we can recast everything in terms of the Q function, IQ functions, the DPP inconsistency, the consistency problems here is taken care of. And then we also have the Q function, that iterative function that we can write, that we can actually have a fixed point that we can approximate, and so on and so forth. We have a Bellman equation that give us a handle to design algorithm, and we don't worry about the consistency because there's also general theories that we can actually borrow here that we have to just change, rebuild. And then the only thing that is left for us is whether we can show that with this shrinking from the state of multi-agent reinforcement learning problem to the state, to network of the state, okay? And then whether this appropriate team Q table can really help us to reduce the complexity. And not only that, we need to be able to provide algorithm that we really can develop sample complexity and convergence analysis. We are mathematicians, so we have to be very careful with that. The first thing that is another surprise for us is also we have to borrow what has been developed, the ideas from graph theory. In graph theory, we all know that whether you learn probability 101, you learn all this graph theory, click through and everything. When you actually have a random graph, and many times you actually try to utilize the random graph properties, you always say sparse graph is better because you can actually utilize certain decay properties to analyze the complexity of the computation. Here, we also need this because when you actually look at this team things, and when you look at this shrinkage from the state from the agent to the state, you need to ensure that there's also efficiency when you actually do it, and you can actually control the error when you actually try to deal with this network. Look at this paper is actually what we really see is this Q function, the team Q functions, they decay exponentially fast with respect to distance. Distance, as I said, is the distance of the node, the number of nodes, the number of edges that are connecting the different nodes. Okay, and that's very important. And not only this is the exponential decay property, has been really used in graph theory. In this particular problem, and I want to say, it's actually embedded in the problem itself. It's not really designed by anything. It's really by this exponential of the payoff function that depends on the team and depends on the neighborhood. And then as the neighborhood gets bigger, the discount factors comes in and cues these errors. Okay, so this is very important. And once we have all these ingredients, then we are ready. So now we say, this is where we actually say, okay, can we actually borrow some ideas? So now we borrow ideas from graph theory, borrow ideas from in-field game. Now can we borrow ideas from machine learning? And of course, for this approximation of the Q function and the value function and also the policy, we take these two layers neural network. The reason we take this two layer is this beautiful work recently showing the two-layer neural networks convergence. Okay, and we want to establish convergence result on that. So we do this overparameterization by these two layers of neural networks to estimate, to learn this policy. And then we also take these truncated Q functions. We know that it has exponential decay properties. And they will also use the same ideas of neural networks to approximate it. And the end result of it, if you combine all these ingredients that I listed here, then you get this. So let me explain. So you get this convergence result with complexity explicit written in this the width of the layers with the batch size and the size of the state and the discount factor, and of course this is T and tractor. These are all the parameters in the models, and this is actually also K. As you see, this K is important. I said the K is neighborhood truncation of Q function. There's exponential decay for the rate in terms of the K. And as you see here, that as the K gets bigger, you do have the K, gamma is between 0 and 1, it actually goes faster. So, however, okay, so this is, of course, explicit expression for the convergence result and the complexity, okay? However, I have to be pessimistic in some way. Even though we have this result here, and we can actually claim that we can do this network papers for multi-agent. If you look at reality, when you think about a general graph, okay, there are different types. One is sparse graph, one is very dense graph. Okay, so the sample complexity will not have too much advantage in a way we do here if you have a very dense complete graph, okay? Because there you cannot really separate very carefully, easily. Everybody is connected to the other in a very dense way. But if you have decent sparse graph, then this is a very efficient algorithm to actually reduce the thing. And now we actually, currently what we are doing here is looking at the real data from California Transportation Department and then try to actually really look at this result, theoretical result, again, is not sufficient. We have to develop more to actually cope with various model complexity and the complexity in the particular problems. And we have to remodel that. But the good thing is these are the basis for which the key elements of the convergence result can be derived. So if you're interested to see some of the earlier works about learning mean field game, so this is this. And if you're interested to see this mean field controls, the earlier works of how the DPP was established, where the counterexamples for this Q function can be found, you can look at this. This is going to appear in OR. And the companion paper that Renee was looking for with the complete mathematical proof is here, where the convergence and complexity analysis has been established and appeared in this SAM journal. And the talk that I'm talking about here, you can find it online, which is about this decentralized network approach for multi-agent reinforcement learning. I think it's time for me to stop so that I can, everyone can actually take a break before the next talk is coming.
Okay, so let's thank Xin for the very interesting talk. So are there any questions from the audience? So maybe I see Peter is, do you have a question?
Yes, I'm just trying to get a view of the speaker. Come on into that for a second. It's a fascinating talk. I certainly found it really, really very interesting. Two natural questions come up in the context of the graph on mean field games ideas, which I presented earlier in the meeting. One is whether, in the limit of having many agents in the local teams, whether that can be interpreted as the local mean fields in the model of graph on mean field games. It would seem to be a natural association, and the question is to identify the states. And the second point is to what extent the notion of critical nodes, which I presented in my talk, whether those can be associated. I did in a game context, whether that can be associated with the position that a taxi driver would like to place his or herself in order to engage with the market. That was one of the motivations. One of the motivating ideas was that an infinitesimal agent would like to place itself at a critical node for its own, of course, for its own advantage in the game. So that these ideas might map into features that have just been presented here.
Yeah, thank you, Peter. Thank you, Peter. This remark is very nice. I really benefit a lot from reading your papers, from many years ago doing mean field game, and also benefit from looking at the videos of your talk. I think indeed there are a lot of, I was actually thinking about it, whether, when we actually have this local Q team things, whether that limit in fact is what you called about the local mean field games.
Yes.
It's something that I was thinking about. I don't think I have the answer, but I think when I watched your talk, and that's one of the reasons actually I emphasize on this so that we can have a dialogue going on, because I didn't even want to do this. I thought, okay, everybody knows about Q, but then I thought about it. I think not only this decomposition is efficient for the Q, for the approximation algorithm, but there's a mathematical structure that could be there. And it's fascinating. I don't have an answer, but I think what you were talking about there was really fascinating. I'm very looking forward to thinking a little bit more about it, and if possible, we can discuss about that. Yeah.
Great.
Yeah. Thank you very much.
Okay, thank you. Let's see if there's any questions from the in-person audience. No one. Let's also check if there's anybody from the virtual participants. Any questions?
I'd like to ask a question if there is time. Thank you for the very interesting talk. So I was wondering, the local distribution, is there a coupling among the across the local distribution, meaning that different agents are counted into the distribution of different local neighborhoods when other agents want to count their local neighbors? So I was wondering if there's there is overlap.
Yeah, very good question. In fact, in this framework, that we really just say, okay, this just need all the agents cross everything are similar, but just also similar to what Peter was saying, that you have this local feature, and that's one of the things we are working on now. Is in fact, when you think about Uber, there are different types of one. The Uber, one of the driver that is full, that is already not taking passenger, and the driver is empty and he's ready to load, or that one driver is actually a sharing driver or so on. So already in a driver, you have the local characteristic, let alone there's also different driver probably charging different fares and so on and so forth. There are local characteristics. And now once you take into account this local characteristic, the danger of that is it suddenly gets very quickly, the complexity increases. So then we have to apply different techniques, what we're actually doing now, to really cut down the complexity to ensure that this, we don't want to do mean field and eventually we get into something that is very similar to multi-agent of the same scale. And so this is something we are exploring now. And I think we will soon have an answer. I think we have the answer, but we haven't written down the complete mathematical proof. But I would be very happy to share with you once we have it, probably in a couple of months. Yeah, very good question. Thank you.
Thank you.
All right, so because I think we have a colloquium at 3, so in case of the time, I'll just cut it here. And let's thank Xin again and all the speakers today.